In this segment, we will be discussing several issues that come up when we do multiple linear regression. The first is this idea of multicolinearity. At the end of the last segment, I talked about how these independent variables ideally aren't supposed to be intercorrelated. There's not supposed to be a correlation between them, but rarely do we find that that's the case. Most of the time we see that all these variables have some degree of correlation. I want to talk about, might be a little bit of a touchy subject, but this idea of salary discrimination and this how it applies to this multicollinearity example. So research in court cases of salary equity have shown the following simple regression, that when we look at salary as the dependent variable, we find that the sex or gender of an individual is statistically significant. And really what we find is that men on average make a higher salary than women. This is commonly reported as this glass ceiling or this salary discrimination issue. This regression might be used to argue for salary discrimination, but there are many other reasons why there might be differences in men and women's salaries that aren't due to discrimination. Some of these, and I'm just suggesting these, women typically self-select into lower paying professions and positions within the same profession. Women may have been out of the workforce due to having children or taking care of elderly family members, so they have fewer years of experience. And there's a myriad of other reasons that we might see, both reasonable and legal reasons for justifying lower pay. So when this argument of sexual discrimination comes up, what we need to do to really validate that argument is we need to control for these other variables that are correlated, have this multicollinearity or this cross correlation with the gender of the individual. So the status or the number of years at work, the type of position. I mean, there's all types of these types of variables that we could include. So if we do this and we control for all these things that increase salary other than just gender, and we do this in a multiple regression, typically we find that sex is no longer significant, but the status and the year's work becomes significant. The interpretation comparing the simple regression and this multiple regression is that there is a mean difference in the salaries between men and women, but this difference is commonly due to other variables that are related to the person's to something other than the person's gender. So once we control for these explanatory variables, sex is no longer significant. This is due to this multicollinearity. In many real data sets, the effect of sex is diminished by including other variables to explain the difference between men and women's salary. However, the variable sex generally remains significant and is often considered to be evidence of possible sexual discrimination. And when we control for these other variables, now you can validate a case for sexual discrimination. So how do we handle multicollinearity when we find it? And I've got to warn you, we almost always find it. If you only are using the model to predict why, then we don't have to worry about it. Who cares if two of the independent variables are explaining the same proportion of y? However, as in the last case with that independent variable sex, if we're using the model to help us understand the relationship and for determining its significant predictor variables, then we need to address the multicollinearity. So if two variables are highly collinear, then we might want to remove one and use only the other one as a predictor variable. Or we might want to use some combination of the two to describe something. How do we identify highly collinear variables? That's where the correlation table comes in. So we look at the correlation table and we don't look at the relationship between the independent and the dependent. We look at the interrelationships between all the independent relationships, or independent variables. So if r squared doesn't, now another way that we can handle this is that when we add variables and the r squared doesn't decrease too much, or excuse me, when we take variables and the r squared doesn't reduce too much, then we aren't losing too much by excluding one variable over another. This is commonly true because if we have two variables that are describing the same portion of the variance of the dependent variable, then taking one out isn't going to affect our test too much. If the r squared does seem to decrease a lot, then the variable is important in the model and we need to find a way to address it. Repeat this process for any predictor variables that you may think are causing too much multicollinearity. However, I'd be careful to do this one variable at a time so that you can identify the best combination or the best variables. There are processes, and there's actually even programs that you can bring into Excel that help you do this, called the stepwise regression. Stepwise regression adds or subtracts, depending on which way you want to go, a variable and runs a regression and compares the results with the new variable added or subtracted. We won't discuss this too much, but that's basically what we'll be doing when we discuss the Gotham cases. We'll be adding variables and thinking about how it affects the overall model. Now, other issues. We want to be very careful about predicting values outside of our data set. So when we used the homes data before, when we have square footage of homes, it's tough to predict about a home that is outside, either very large or very small, outside of our linear regression. And this is what I'm talking about here. If our data is in this range, it would be very difficult to predict the selling price of a home because we don't know the relationship that occurs beyond where we have information. If we find that a set of predictor variables is not significant and some are, should we rerun the regression with only significant variables? Once again, if our purpose is for prediction, then we could probably leave all the variables in because they are probably all increasing our predictive ability at least a little bit. It's not costing us anything to keep it in there. However, if for understanding the relationships and the hypothesis testing, we want to find, after controlling for these other things, what is the relationship, then we need to be careful with adjusting for and watching for this multicollinearity. We might want to remove some of these variables that don't have predictive value, but don't rerun the analysis without non-significant variables and check the r squared. Rerun the analysis without the non-significant variables and check that the r squared doesn't decrease too much. Do not make your decision about which variables should or should not be included simply on the t-test.